Welcome to Hot Chips 28. Session 8, Dealing with Big Data.
Good afternoon. I'm Chris Rowan. I'm chairing this next session on big data. And big data has taken on a number of important meanings. There's both really the classical, you might call it the old school, big database part of big data, and we have two excellent talks on that. But also there are new trends in big data, especially how we start applying new computational models like deep learning to big data. And the first of our talks is from David Moloney of Movidius on big data in the context of deep learning. David has a wealth of international experience at Infineon, at STMicro, at CEVA DSP. He has a PhD from Trinity College Dublin on high-performance computer architecture, awarded in 2010. David co-founded Movidius in 2005 with the vision of enabling high-performance embedded numerical applications like vision processing. And he's going to talk both about the fundamentals of that technology and some of the product implications that make it fast and efficient. So please welcome David Moloney.
So thank you, Chris, for the kind introduction. I guess the session here is about big data, but I guess you could classify what Movidius is doing as kind of small data, so inference at the edge. And I'll try and explain today, what we're doing to help people, researchers and practitioners, in terms of getting their networks from training in the cloud, on workstations, and into mobile devices that can have a view of the world, so you're close to the sensors. So, I'm sure you'll have all seen. In fact, we have it outside. We have a DJI who've introduced a world-leading, and in fact, the first autonomous quadcopter based on our technology. And I think that's typical of what's going to come, in that you very quickly after DJI announced their product, you saw people like SenseFly and Yuntech and so on, a host of others, in fact, announcing similar products. So I think as we go forwards, things like megahertz, megapixels, megabytes are going to become less important, and product intelligence is going to become more important, particularly with the asymptote of Moore's law in view. On the right-hand side of the slide there, you can see basically how in the case of, let's say, deep learning-enabled products, Tesla has been able to overtake everything else in the market and really grab mindshare by having deep learning-enabled products. So they're, for many companies who have brand and channels to market and so on, having or not having machine learning enabled products may end up being critical to the survival of their efforts and their products in the marketplace. So, let's say this diagram here really shows what's involved in, at a very kind of high level, what's involved in training a deep network. And this is what people like NVIDIA and Intel and other people in the audience are doing in terms of accelerating this. So there are huge numbers of calculations. In fact, you need to do multiple inferences inside a feedback loop driven by error compared to the input labels in order to take a series of input images typically, but it could be speech or other data that's been labeled typically by humans, and to produce the correct classifications at the output. And those networks consist typically of multiple layers, and in fact the number of layers has been increasing. We'll talk a bit more about that. But let's say from an overall perspective, within each one of those layers you're going to have convolution, you're going to have kind of 2D downsampling of one kind or another, typically called pooling in deep learning language, and you'll have some kind of activation function, a nonlinear function, let's say a bit like a half-wave rectifier in an electrical circuit. But bottom line, this is really what you want to do. So you want to train once and infer many times, and this is what a lot of people want to do. Let's say with things like drones, to be able to push networks that have been trained in the cloud into the devices in the field in order to give capabilities, give new capabilities to the device that it previously didn't have, and that these, a bit like what Tesla have done with the self-driving car feature, which is deep learning enabled, that effectively you can overtake everybody else in the market, if you forgive the pun. So, if you look at the trend here, AlexNet was, it seems like eons ago, but it was only introduced in 2012. 2013, VGG from the group in Oxford, and GoogleNet appeared in 2014, ResNet now with Microsoft in 2015, and you can see the number of layers has gone 8, 16, 58, and 158. The accuracy in that time, even though the number of layers has gone up massively, the accuracy has gone up basically just over 10%. So there's definitely, deeper is definitely better from an accuracy point of view, but from an embedded point of view, accuracy isn't everything, because if you have a network that you can run for an hour in an always-on application, it means you're going to run out and change the battery every hour. So what makes sense from a training standpoint in the cloud, and what makes sense from a big data point of view, from a small data point of view, may not be necessarily the right thing. And again, we'll come back to that later on in the presentation. So if you look at something like GoogleNet compared to AlexNet, so there's a kind of in 2 years, the computational cost, the accuracy increased about 10%, the computational cost increased 2x, and you're kind of at 1.5 billion operations per evaluation or inference, and around 5 million parameters or weights. And let's say it's composed of many layers, but let's say there's kind of 9 major functional layers in there, and you can see convolution that we spoke about is represented in blue, pooling in orange, pooling here, and softmax, which is kind of nonlinear function, in this kind of lighter orange color here. And you can see there, it's kind of there's a repeated modular structure, and this is typical of the other nets that have been introduced since, things like VGG and like ResNet from Microsoft. So if you look at what's required for small data inference at the edge, where you want to take a network that you've trained in the cloud and deploy it across hundreds of thousands or millions of devices, one of the big considerations is energy. And Mark Horowitz from Stanford at ISSCC a few years ago in 2014 talked about the amount of energy required to perform let's say a computation A plus B, register to register on die is maybe 1 million x less than what is required to transmit that data off a mobile device over, let's say, LTE or Wi-Fi. So you need to think, from a global energy perspective, where does it make sense in that context to do the computation? Does it make sense to transmit the data off board, or do you process locally? And certainly with numbers like that, you would be trying to process locally. The other question is the amount of bandwidth consumed. So let's say, assume that energy wasn't a consideration. Well, the bandwidth, Margaret Martinozzi's group in Princeton did a study where they showed that they could synchronize cars using a very simple computer vision algorithm to traffic lights. So simple orange, green, red detector. And what they found was that if you implemented all of that in the cloud, it required about 10,000 times more bandwidth than computing the result and just sending up 30 bytes of metadata every few seconds. Another issue is latency, and again, there was a keynote from Google at ISSCC in 2014 where they had a call to action for latency in data centers. And if you have a self-driving car or something like that, you simply can't tolerate the latency of going to the cloud to figure out, is that a pedestrian, because the person is already dead by the time you've figured out that you need to hit the brakes. And other kind of elephants in the room are really, fault tolerance or continuity of service in the event that, let's say, you're reliant on the cloud. If for some reason or other you get a network outage, then your product doesn't work. Let's say a security camera is trying to moderate access to the facility. And if your network goes down, you can no longer do inference, and you either can't let people in the building or let people who shouldn't be in the building in. And of course, privacy is a huge concern. So very, very much the premise that we're operating on is that you want to do inference as close as possible to the sensors for all of those reasons. Not least of which is the bandwidth reason, which means if you want to deploy this kind of service, even assuming energy wasn't a problem, if you want to deploy a new service that's computer vision, or in this case deep learning enabled, if you cannot do that without increasing the amount of infrastructure before you can launch the service, you're kind of in trouble. So with those kind of numbers, it's very important, we believe, to push inference to the network edge. So in terms of, this is the device that we're showing outside. It's the device that's powering the Phantom 4 drone. And you can see where the performance is coming from is from the 12 onboard vector processors and from these hardware filters, including a 5x5 convolution block that can be used to increase the performance of CNNs. And all of this is basically accesses a high bandwidth memory subsystem that consists of 64-bit wide blocks of memory operating 600 megahertz, delivering an aggregate 308 gigabytes per second of memory bandwidth. So this allows you to kind of mix hardware filters with blocks implemented in software running on the Shave processors. All of these are 128-bit vector processors, and for inference, it's important. You don't need to go off out of package. We have a stacked DDR device in package, so it's the device we're showing on our Fathom stick outside is a 512 megabyte LPDDR3 device. So you can take very large scale networks, and in fact more than one of them, and store the associated weights and the binary corresponding to the network in the DRAM. So one of the things is you can obviously do 32-bit inference, or you can in fact do 16-bit inference on existing GPUs. Pete Warden of the TensorFlow team pointed in posts this year to how you can implement networks using 8-bit. So from the point of view of maximizing the performance here on Myriad, what we did, rather than do 32-bit inference or 16-bit inference, was to look at a kind of a mixed approach where we do partial multiplications in 8-bit, use integer, and then we can accumulate results in 32-bit. So we have, within the Shave, we have 8 functional units: predication unit, branch and repeat, 2 load stores, integer, scalar, vector, and compare and move unit. What we found was that in order to maximize the performance, what we did was a kind of a two-row partial multiplication for a matrix product, doing 8-bit max using the VAU and 32-bit partial summation using the SAU and IAU. So essentially here, using the vector unit, we're able to perform the vector multiplications for all of the initial products here in 8-bit. We can do the summations associated with those, so basically across the product there. And we can then do accumulation in the IOU of 32 bits. And the fact that we have lots of ports on our register files means that it's very practical to do that. And then we have the loads and stores parallel with that, and we can do a zero overhead loop using the branch and repeat unit. And essentially what that delivers is basically 32 operations per cycle at 600 megahertz in the VAU, 15 operations per cycle in the SAU, 1 operation per cycle in the IAU. So total 48 operations per cycle on the 12 sheaves at 600 megahertz gives us a maximum theoretical of 345 gigaops per second, and with let's say in terms of implementation loss compared to doing this in 32-bit, it's bounded in probably in the order of 1%. So essentially, what we did then was to compare what we can do in terms of the performance with the device that we have here compared to the kind of straight line path from taking networks that are trained in the cloud and deploying them. So compared to other devices that are available, we're talking about less than 1.2 watts TDP. This is for GoogleNet v3, and we can do inference at 25. So it's roughly, let's say, 20 to 25 inferences per second per watt, and kind of gigaflops per watt figure, equivalent to around about 71 gigaflops per watt. So again, this makes it possible with silicon that's available right now to do very high performance inference using state-of-the-art networks like GoogleNet v3 without a fan and without a heatsink. So the kind of things that we're doing in terms of simplifying the path from taking a network that has been trained on and getting it onto the silicon is to develop some tools and a optimized library we call MV Tensor that implements that kind of 8-bit kernel arithmetic for matrix products, and to implement the other various kernel functions that you need. Run those on the shaves. We have the option of further accelerating using the 5x5 convolution block. But the most important thing, I think, is being able to get from a network quickly that you've trained in the cloud to something that you can deploy in an embedded device, basically using a push-button flow. So you don't need to be an expert in programming embedded platforms in order to deploy, to develop this network and then deploy it, let's say, in a security camera or some other device. So one very interesting thing that I alluded to earlier on is in terms of what is it costing us if we take these networks and deploy them. So what we did was across a range of different platforms. So this is an Exynos application processor, TK1, TX1, x86, and K40. So this is basically from server grade infrastructure to mobile platforms to look at, well, what does this cost what does the 10% or 12% accuracy cost us in terms of energy. And you'll see in line with the architectural trend here, the number of layers in the networks has been going up, whereas the number, the energy has been going down. So roughly what we've seen, and it's consistent across platforms with the exception, I think, of the x86. I think that the x86 is probably more like load store bandwidth for Xeons is an issue for this kind of network. But for the other platforms, it's pretty clear that what you're paying for that 10% accuracy increase is probably 2x in terms of power. The reason for that is basically the increased number of layers means that you have more energy being expended on loading and storing those intermediate results to and from DRAM. And in fact, I see Bill Daly up in the audience there, and Bill's own research pointed to this, that one of the key areas that you need to optimize for in terms of SoC design and in the associated program design is to minimize, first of all, DRAM accesses, then memory accesses, and essentially try and trade arithmetic operations for memory, for reduced memory access. So I think the point here that's of interest is that I think there's still lots of scope within the design of neural networks to produce networks that have a high return in terms of accuracy for every watt or joule of energy that you put into them. And currently, the ImageNet style competition is not really taking power into account, and as such, I think there's very fertile scope there for optimization in that area. That's certainly something that we're interested in ourselves. So I think, to summarize, when you want to deploy these kind of networks in, let's say, in a small data scenario where you want to do inference in mobile devices using networks that you've designed in the cloud, it becomes all about inference and not training, because essentially you do the training once and then infer many times. The standard networks that are out there are very much designed to produce highly accurate results, but they haven't been designed with a view to getting a good energy return. So certainly when it comes to battery-powered equipment, there's lots of scope for producing networks that produce a better return on accuracy, in accuracy terms, for every joule of energy you put into them. And we believe that right now that the solution that we're providing is good in terms of getting to the first phase of the deployment of these networks. I think there's much more to come in terms of changing the hardware-software mix over time as the understanding of these networks improves. And the big challenge here from a hardware and a software point of view is to optimize networks from the point of view of performance per watt. So that concludes my talk. So any questions, we'd be happy to take them.
Thank you very much. So we do have time for a few questions. If you want to line up, please go ahead.
Hi, Alex Burt, Qualcomm. So you have a total potential performance of 350 gigaflops.
Yeah.
So, but on GoogleNet, you only achieve 80.
Yeah.
This type of ratio of 25-30%, that's more like a GPUs who are not designed for deep learning. Yeah. But you design special machines, so why you only have one?
Yeah, we didn't design a special machine for deep learning is the answer to that question. So we designed for computer vision, but not for deep learning. I think what we're doing is learning from what we've deployed in the field. I mean, this device is being used in devices, and it's being used to deploy deep networks today. And for sure, that'll make its way into our next generation product. But it's like anything. I mean, you have to learn to walk before you can run. So
what do you think are the biggest bottlenecks right now to get to them?
The bottlenecks in terms of our architecture, I mean, I think it's not raw arithmetic performance in these kind of systems. It's always about sustaining the arithmetic performance. So I think the big issue is in terms of having a good enough memory storage hierarchy so you can sustain this kind of performance.
Thank you.
Yeah. And just one other thing is that what I showed there in terms of that peak performance is just for the inner loop. There's obviously code that goes around that. So apart from any issues in terms of memory hierarchy and so on, a kernel doesn't necessarily correspond to what you get from an overall application.
Yeah. Over here.
The question here is, do you see in the next 3 to 5 years that the hardware acceleration will be able to push the accuracy up to about 99%?
Well, I think accuracy-wise, you're going to get there, but you're going to continue to increase accuracy. But the current next network design paradigm is such that you're not going to be able to do that linearly in terms of energy. From my own point of view, I think the process of designing networks is still immature. It's not, let's say a lot of people in here in the room are used to doing signal processing. Information theory and DSP is very well understood. I don't think that applies the same way to CNNs, and I'd expect to see a big, as more engineers here in the room get engaged in the process of designing hardware or hardware and software for CNNs, I'd expect we'll all bring to bear our significant brain power on this topic. And we're obviously, as hardware engineers, we're probably much more motivated to understand how to get a better energy return than somebody who's just doing this from a software perspective.
Well, very good. Let's thank David once more.
Thank you. Thanks, Chris.
Our next talk is from Oracle, and we have a tag team consisting of Aingaran, who is the director of software in silicon at Oracle. His team works with groups across different levels of hardware-software stack to build special-purpose hardware accelerators. Aings has worked in several generations of SPARC processors and multimedia chips. His interests are in hardware-software co-design and processor architectures for low-power compute. He has an MSEE from Stanford and is a senior member of the IEEE. And his partner in this talk is David Lutz, who's a principal software engineer in performance technologies at Oracle. He specializes in database and file system performance optimization. His current focus is on Oracle database in-memory option and software in silicon that you'll hear more about. David joined Oracle via Sun in 1998. So please welcome Aings and then David. Thank you.
Thank you, Chris. So I'm here to talk about software in silicon in the Oracle SPARC M7. And please don't sue Oracle based on anything I say today. So I'm going to first describe what software in silicon is and the motivation for putting it in our processor. And then I'll go into some details on the features that we call software in silicon. And after that, David will talk about the hardware-software stack, and he'll discuss some performance measures on the Oracle database and on other applications. So the Oracle SPARC M7 is a 32-core processor, SPARC processor that was presented previously in Hot Chips. And today I'm going to talk about special custom hardware that's inside this processor, which captures functionality that was traditionally implemented in high-level layers of software. So it's high-level software functionality that's captured in the silicon in hardware. And this falls into three categories, which I will go into details later, but the categories are security in silicon, SQL in silicon, and capacity in silicon. So the reasons for doing software in silicon are twofold. On the one hand, we have the challenges of scaling frequency and technology and power dissipation that everyone here is probably very familiar with. And the way around that is to build special custom power-efficient hardware that's targeted at certain interesting applications with the goal of keeping those applications on the exponential performance curve that we are all used to, even if it's at the cost of some other applications. And on the other hand, there are market pressures that are also pushing in this direction. Primarily, it's a shift in what computers are used for in the industry. They used to be used primarily for analytics, and now we are moving more to they used to be used for transactions. We are moving more towards analytics. And analytics applications are extremely parallel, and also they involve, at least from a computer architect's point of view, relatively simple compute operations that are very amenable to acceleration. So on top of that, there's also the shift from spinning disk storage to solid-state storage, which again is moving the bottleneck from storage access latencies, which are hard to accelerate, to compute latencies, which are easy to accelerate. So in Oracle, we've taken advantage of the fact that we are a full-stack company and we have visibility into multiple levels of software to capture functionality from different levels into the hardware. So let's look at some of the candidates for this kind of acceleration. The first, like I said earlier, is analytics. So if you look at a typical analytics benchmark that's shown here, excuse me. If you read this statement from bottom to top, you can get an idea of what's going on. And what's happening is it starts out with a set of filters in red and orange. And what this is trying to do is it's looking at a large data warehouse, and it's trying to discard all the data that's not needed for this query. So it's a simple filtering operations. And then we move on to more complicated filters. And then finally, we move to joins and grouping operations, which are harder to accelerate and are more complicated operations. And after that, it's a reduce operation, which again is a simple arithmetic operation. So the ones marked with an asterisk are easy candidates for acceleration. And if we look at another layer of the software stack, compression and decompression are also good candidates, and they help reduce the memory footprint. And similarly, security is a good candidate that gives a lot of value to the final system. So I'll talk about security first, or security in silicon. And this is two components. The first is called encryption in silicon, which is just hardware acceleration of standard encryption, hashing, and public key infrastructure. And the other component is silicon secured memory, which is a hardware-based coloring scheme. And what it does is all data that's in memory is assigned a certain color, and hardware allows access to data only if a reference is presented with a matching color. So if the color does not match, for example, if you use a stale pointer that doesn't have a matching color, the hardware would flag an error. And the SPARC M7 has support for up to 14 colors. So let's take a look at an example. Suppose we had a buffer overflow attack like Heartbleed, where we have a server that has a certain vulnerability, and there are two clients connected to the server. So what happens is one client breaches the memory allocated to it and looks into the memory assigned to the other client. If this server was running on a machine with with silicon secured memory, this attack could be detected by the hardware, because the first client would be given data that's given a region of memory that's colored green. The second client would be given data that's colored blue. And if the blue client tries to breach the green client's data, the hardware would detect it and stop that. So we have run several transaction workloads with silicon secured memory enabled, and we see no performance degradation for using it. So the next component is SQL in silicon, which is analytics acceleration. And this is done in a special hardware block called the Data Analytics Accelerator, or DAX. So the DAX is like a stream processor, the DAX is like a stream processor which consists of 4 independent pipes which can each execute commands in parallel. And in the SPARC M7, there are a total of 8 DAXs, so for a total of 32 pipes. And the way these pipes work is like a DSP processor, sort of. They implement a series of filters which map to the filters I showed you earlier. So if you look at the typical commands executed by the DAX, the scan command implements a simple search. So let's say you were running a query where you were shopping for a car. You could use the scan command to narrow down your search to just the make you were interested in. And similarly, the translate command implements a set intersect operation, or implements a Bloom filter which can be used to do a set intersect operation. So for example, once you've identified all the Toyota dealers, you may want to intersect that set with all the dealers in San Jose to find a dealer near you. The select command is a filtering operation that takes the data that's been marked by the previous commands and actually discards the data. And then we have other commands which do format conversions, usually from storage-friendly formats to compute-friendly formats. The last feature is capacity in silicon, which is an inline decompression scheme. So this is done with a special compression algorithm called OZIP, which was developed by the hardware and software teams in Oracle. And it was developed with the explicit purpose of making the decompression step as easy and fast as possible in hardware. And it gives about a 2 to 5x compression ratio. But because the decompression is so fast, the decompression actually runs at very close to memory speed. And because it's so fast, it can be done in line. And since it can be done in line, the previous DAX commands that I described to you can actually run directly on compressed data because they can be decompressed in line. And this means that the overall memory footprint is reduced. So next, David will describe the hardware-software interactions and some performance measurements. David?
Great, thanks, Dax. Thanks, Angs. So I'm going to start off. I'm going to talk a little bit about the hardware-software stack, and then I'll go through some use case examples with some performance measurements on various use cases. Oops, sorry, I went the wrong way. OK, so starting with the hardware-software stack, this is the basic DAX programming model. In general, when you make calls into the DAX, you can think of it similar as a system call. You're passing off a request that gets passed down through the stack, acted on for you, and then results are returned. So when an application wants to make use of the DAX, when it's going to send a request out, first it prepares its inputs, which are going to be passed through the API in shared memory. And this is basically flags and memory references that you get passed down. The API is going to send the request down through the operating system layer to the hypervisor, which presents a virtualized view of the DAX, also does the scheduling of requests across the different DAXs in the system, and also manages access among multiple domains if there are multiple domains in the environment. So then the request goes out on the DAX hardware, gets executed. Results are then passed back through shared memory again. And the client when the client's ready to wait for the result or check on the result, it does so with an M-wait, which is a very lightweight signaling mechanism, which parks the thread while it's waiting. The libdax API itself hides all the technical details of the communication, provides the architectural invariant, so you can write to the API, and then it will run on any of our systems that have DAX hardware. It's easily called from multiple languages. It's thread safe. You can have multiple threads using it at the same application in the same process. And we also provide both synchronous and asynchronous versions of the various calls. Okay, moving on to some use case examples. Start out with Oracle Database in Memory. This is an example where we've done all the integration for you. You don't have to do anything special to take advantage of the DAX. You configure Oracle in memory on a system with a DAX like you would on any other system. At runtime, we automatically detect the platform. We load the best available library. On a DAX-enabled system, we're going to load a DAX-enabled library. We're going to automatically do the query acceleration for you. Administrator doesn't have to do anything special because there's a DAX. There's no query changes that are required, and no application changes. So what is Oracle in-memory database? So databases traditionally store data on disk in row major format, which is optimal for the single row access, which is typical of an online transaction processing system. What Oracle Database in-memory does is it provides an in-memory column store, which is simultaneously active and transactionally consistent with the on-disk image. And the in-memory store is stored in column major format, which is optimal for data warehouse and analytics processing, and also is excellent format for us to use accelerators like the DAX. So how does a database administrator enable Oracle in-memory? It's pretty simple, really. Basically, for an object in the database, like a table or a partition, they just set an attribute that says this object should be enabled for in-memory. They can optionally set a compression level as well, or a memcompress level on the object. And basically what those do is they define a set of heuristics which the database will then apply to the data, and basically the heuristics say how to optimize for versus space versus query performance. And generally, as you go down this list, we're adding more options with higher level compression and heavier weight encodings. So the three most important ones on this list are memcompress for query low, which is the default. That enables a number of different bit and byte pack formats and some use of RLE. They can go to query high, which enables more use of RLE. And on systems that have a DAX, we also will enable OZIP compression. And in this case, the database uses OZIP in a way that allows us to take advantage of the scan and decompress in one step that Ang's mentioned. You could also go the next level higher, which is capacity low. In that case, we also use OZIP, but in this case, we use it slightly differently. We get a little bit more compression out of it. And in that case, we need to do a scan, a decompress first, and then a scan. So we do a two-pass operation, but it's still, both operations are accelerated by the hardware. Moving beyond the database, we have the libdax API. And a published stable version of the API is available today on our Software and Silicon Developer Portal, and it will be available in a Solaris 11 update release expected later this calendar year. So this library provides all the building blocks that an application needs to use to take advantage of the DAX, including an OZIP compression library, so that they can do the compression in software and then take later advantage of decompression in hardware. So you can go to swissdev.oracle.com and apply for an account there. It gives you access to the API and documentation, and also access to DAX-enabled hardware to try it out yourself. Okay, now moving into results, I'll start with Oracle Database in memory and start with some micro results first. So this slide has some performance and efficiency measures. These are based on timing traces of individual operations, subcomponents of queries, and it's based on a comparison of a generic C code library versus a DAX accelerated library. This result is the aggregation of 16 different analytic queries that are all run against scale factor 1000 star schema benchmark. Star schema benchmark is a benchmark that was developed outside Oracle. There's a URL at the bottom of the slide. You can go and read about it if you want. It's basically a data warehouse analytics workload. So these results are the aggregate results of 16 different queries working against different columns. So there's different bit and byte packed encoding levels that are involved here. So the upper left-hand corner shows the speed up on scan processing, and this is when we're scanning a column for rows that match a single value. And we're seeing a 23x speed up in that case. Upper right-hand corner is scan range, so now we're scanning that column for a range of values, and in that case we got a 17x speed up. Lower left corner is translate, and that's the Bloom filter operation that Ang's mentioned, and we use that when we're joining big tables to small tables typically, and we saw a 10x speed up there. And then the lower right-hand corner is for select, and that's where we're actually returning results of a query back up to the upper layers of the database. And in that case, we got a 30% speed up on that. Moving on to decompression, the previous slide, none of that data was compressed. It was encoded in bit bit and byte packed and stuff like that. But moving on to compression with OZIP and RLE, we got an 8x speed up in RLE burst, which is run length encoding, decompression, and then an 11x speed up on OZIP decompression. And again, just to mention, the administrator doesn't pick, at least in the database, doesn't pick RLE or OZIP or any of the other encodings. They set these heuristics, and the database is automatically going to analyze the data itself on each individual column and pick the most appropriate encoding based on the heuristic. Okay, moving on to a full stack comparison, still with Oracle in memory. This is a generational comparison of SPARC M7 versus our previous generation SPARC T5. It's a comparison with two 4-socket servers, M7 and T5, both running Solaris 11.3, both running Oracle 12c. The workload is based, again, on our 1,000 scale factor star schema benchmark. It's a little less than 700 gigabytes on disk, uncompressed. All the tables are configured mem-compressed for capacity low in this case, which gives us OZIP compression on both platforms. So it gives us our best apples-to-apples comparison when we're taking full advantage of the DACs. The workload itself is a set of analytic queries that we run against the database, and we run multiple copies of multiple queries simultaneously until we have 4 processes per core on both platforms. And our key performance metric here is queries per hour. So this slide has performance and efficiency measures of this comparison. So again, the SPARC 4-socket M7 versus 4-socket T5. Upper left-hand corner is the overall performance gain. So for this workload, we got a 9x gain in throughput in queries per hour on the M7. Upper right-hand corner is a power efficiency measure. So here we got an 11x gain in performance per watt for this workload on the M7. Lower left corner is a thermal efficiency measure. And here we got a 14x gain in performance, total throughput of the chip relative to the temperature of the chip. And then finally, the lower right-hand corner shows the benefits of offloading work from the core to the DACs. In this case, we got a 3x reduction in core utilization while getting a 9x gain in throughput. So that reduction in core utilization frees up the cores for other processing to take place. Okay, moving on to some additional workloads beyond the database. We have some use cases from our Software and Silicon Developer Portal, and a few different examples here. These examples are all available. The software is on the developer portal, so you can go online and you can see the examples. You can run the code yourself. You can check out the code. So a few different examples. K nearest neighbor, top N, a couple others, and in general, seeing a 4x to 12x gain in performance on these algorithms, depending on the algorithm itself, the data set size, and things like that. So the thing here as well is that we get performance gains on here in at least two ways. One is that in some cases the DAX is accelerating like a core component of the algorithm itself, like just SQL scanning for JSON data. Other cases, we're using the DAX to filter down the original data set size to a smaller data set size, so that when we apply the complex algorithm, it's much faster overall. And also, just to mention, these examples are in multiple different languages, and again, you can see the examples running yourself on our developer portal. So one final example. This is an example for one of our partners. Worked with our engineers to, Quartet FS worked with our engineers to help them use the DAX API to accelerate their in-memory analytic query workload. In this case, they reported back a 6x to 8x gain in performance on these queries, while simultaneously getting a 2x to 8x reduction in core utilization. Okay, to summarize, so software and silicon, what we consider software and silicon is custom hardware that's targeted at specific high-level functions that would normally be implemented in software and implemented in hardware instead. We see a lot of opportunities out there for database and analytics and big data across the board for capturing more functions like these in silicon. With SPARC M7, I should also mention that the newly released SPARC S7 has these same features. It's just a smaller footprint processor, but it has the same DAX, has all the same features that we've been talking about. And so with this current implementation, we're seeing gains in performance, power, security, and memory capacity. Oracle Database takes care of this fully automatically, and obviously we'll look for further opportunities to do the same kind of thing. And also we have this API available that anybody can use to take advantage of the DAX to speed up their analytic processing. And finally, of course, we're continuing to research additional opportunities for even tighter hardware-software co-design and try to achieve even deeper gains on a broader set of applications. So that's all we've got. So thank you very much.
So thanks very much, and I do think we have some time for questions. Let's start over here this time.
Thank you. Question is about the power consumption and the scalability. The first thing is how much power would a 4-socket configuration burn? Second part is would the scalability of the performance of the analytics scale up linearly, say after 4-socket, 8-socket, or 16-socket, that kind of configuration? Would that be linear or be nonlinear?
So on the question of power, I'm afraid that's Oracle regards that as a trade secret, so I can't discuss that.
Understood.
And on the scaling question,
the second half of the question, the scalability, absolutely. These workloads scale. Oracle in memory is kind of inherently can potentially be inherently parallel, and we get really excellent scalability. Across these multi-socket servers, we have excellent memory bandwidth, which is one of the keys. And so yeah, this stuff scales excellent.
Linearly or non-linearly?
Linear. Yeah, it's pretty darn good. Linear scalability out to 16 sockets is and it depends on how you do it. If you have you can scale in multiple ways. One is, you have one big system and you're scaling out lots of processes on that one Solaris image. You can also scale it out by carving it up into multiple domains. And in that sense, it's actually easier to get linear scaling on at that level. But we get excellent scalability even with a single system image.
Thank you.
Mm-hmm.
Let's take one question over here.
Right, Long from Huawei. So I have a few questions. So DAX support a few query operations. Are you going to support more complicated operations in the future design?
that is the plan, yes.
All right. And another thing is in the slides you show for the simple operations, most of them achieve like more than 10x speed up. But for select, you achieve like 30%. So what's the reason behind that?
So, there's a couple things, and one is actually, with the other operations, you're basically going to churn through very, very large amount of data, and so there's a bigger opportunity for you to speed that up. And for the select operation, in the best case on the software side, you may have a relatively few number of memory addresses, and you can go fetch them. And on the hardware side, we're going to look at a bit mask and decide what we're going to send back. And actually, the cutoff point is extremely low. It's less than 1% of the results going back get you a speed up in the hardware. But in that particular case, the amount of work to do the select is potentially not that much in the software side in some cases.
All right, last question. So for the CPU utilization, you showed we have a great reduction. But how about the DAX utilization in this case? the question actually is why you choose 32 pipelines?
Why is the question why we chose 32 pipelines?
Yeah, actually, so one part of the question is how's the DAX utilization in your benchmarks, and another one is why you decide to use 32. Are you going to do like stick to 1-to-1 core to DAX mapping, or you have some other?
So I don't actually have the DAX utilization numbers, but regarding the question of 32, I think that's a good question, and there's a lot of work on evaluating the right balance on a many-core system between the different types of compute you have. In our case, actually, it was easy. We chose the number that would saturate memory bandwidth, and that just happened to be 32.
All right, thank you.
Let's just have one last question, please.
Okay, I'll try to make it simple. Nathan Brookwood, Insight 64. You've got millions and millions of lines of code in an Oracle database system and thousands of different modules. How do you figure out, is there a process that you use, methodology you use, to find the places where the maximum benefit could come by migrating functions from software to silicon?
I think that's a break time conversation. I couldn't answer that
I thought it was simple.
It's not. Yeah, go ahead.
It's a combination of profiling and tracing is one of the key things that you're doing. You're profiling the workload and finding out where you're spending time doing tracing. You have people looking at the algorithms themselves, and so it's really there's a lot of things that you do, but profiling, tracing, algorithm analysis.
So it's all basically data-driven, is what you're saying.
Sure.
Yes.
Yeah.
All right. Let's thank David and Angs.
Thank you.
Thanks. All right. So the third talk of this section is from Jian Ouyang, who's a principal architect of Baidu. He got a master's degree from the University of Science and Technology of China in 2009. He joined Baidu that year, and he now leads the team looking at new architecture and systems for self-driving cars and data center. Please welcome Jian.
Thank you. Thank you, Chris, very much. Good afternoon, everyone. My name is Jian Ouyang. I am the principal architect from Baidu. Today, my presentation is SDA, the software-defined accelerator for general-purpose big data analysis system. And I believe the big data and AI is the two fundamental components for many applications. So, 2 years ago, I have presented the SDA for AI in the hot chips, and today I present the big data. And again, before the presentation, let me give a brief introduction of Baidu. As we know, Baidu is the biggest search engine in China. And today, beyond the search engine, Baidu is developing the new business, such as the autonomous car, O2O, cloud. And all this business is driven by the AI and big data. So you can know the background of our work. So I lead a team to build a new system and the new architecture for the data center and for the autonomous car. This is the outline of today's presentation. First, I will give the overview of the big data and its system. And then I will present the motivation and the challenge of accelerating the big data. And I propose our solution, the SDA software-defined accelerator for big data, including the design goals, the implementation, and the performance evaluation. And at last, I give the brief conclusion. As we know, big data means the data is big. This is the common sense. And I will take Baidu as an example to demonstrate how big it is. We had about 1 EB total data in Baidu, and we had to process about 100 PB data per day, and our search engine had to handle about 10 billion requests per day. This slide can give you a high-level overview of the stack of the big data. In the bottom layer is the system architecture. We have built a large-scale data center, networking, server cluster. And on the hardware, we have built large-scale software infrastructure, including the data center OS, real-time storage, and real-time computing. And the middle layer is the data management, such as the data warehousing and machine learning. On the top level, there are lots of valuable applications. For example, the knowledge graph, multimedia, NLP, and CTR. So we can see that the applications are diverse and the systems are very complex. Due to the complexity of the system and the huge column of the data, so we need huge compute capability to process the data. I think the computing requirement equals to the data scale multiplied the algorithm complexity. And there are some obvious changes. Firstly, the data scale increases rapidly. And second, the algorithm complexity also increases rapidly. But I think the performance of the general purpose CPU increases slowly. We can see the figure from 2009 to 2015. The performance of CPU increased 4 times. In 2009, the typical configuration of CPU in data center is a dual core running at 3 GHz. And in 2015, the typical configuration is a core running at 2 GHz. And at the same time, the scale of the search engine business increased 15 times. I think the number for CPU is not very exact, but it represents the change. The change is that the CPU moves slowly than the need of application. So we had to accelerate the big data processing to bridge the gap. But during we found some challenge of accelerating the general purpose big data. Firstly, we found that it's difficult to abstract the computing kernel. As I mentioned before, the applications are very diverse, and there are valuable computing time. And second, it's difficult to integrate the accelerator to the distributed system. There are valuable platform and program models, such as the Movidius, SPARC, streaming, and lots of the user-defined program model. And additionally, there are valuable data type and storage format. So we proposed the SDA, the software-defined accelerator, to address this challenge. According to our observation, we found that about 14% of the data analyst jobs is written in SQL, and most of data analyst jobs can be written in SQL. And there are lots of the popular SQL systems. For example, the Hive, SPARC SQL, and Impala. So I think the SQL system can represent some kind of the general purpose big data system. So there are 2 design goals for the SDA. First is that the design goal, the SDA focus on the SQL system, because the SQL can hide the diversity of the application. And the SDA should be easily integrated into the popular distributed system, for example, the SPARC SQL. The next several slides is about the design. And the first is that we abstract the SQL kernel to the hardware architecture. The figure is a real query from the TBCDS benchmark. We can see that we can abstract the query into 5 base operations: the aggregate, join, filter, group by, and sorting. We also analyze the order of the queries from TBCDS and the real workload from Baidu. We can generalize that all the SQL operations can be abstract to 5 basic operations. And the SDA supports all the data type of the TBCDS, especially it supports the variable length stream. It's very important for the accelerator. I think it's the first of all to support the variable length gym in the accelerator. And this is the overview of the system. The SDA is the hardware and software co-design system. The SQL query should be transferred into the several base operation, and the transformer layer includes several layers. For example, the parser, analyzer, optimizer, and plan. And the command of operation is from the API and driver to the hardware. There are lots of the PE processor element in the hardware. Each PE is for one kind of the operation. For example, the PE for filter, PE for join. And we use the data flow program model for the SDA. The data flow program model is very common in the distributed system. And the data block lists in the onboard data memory. And the data block is stored on column-based. Column-based store format is very common in the distributed system. So it's very easy to integrate the accelerator to the distributed system. And when the job starts, the PE load the data from object memory and process data and write back the result to the object memory, and then trigger another operation. So it reduces the communication between the host and the accelerator. But if there are some operation that the SDA cannot support, the data should copy back to the host. And if the software operation occurs, the data also should copy back to the host, because today the SDA cannot support the software. And this is the hardware architecture. We use the PE-based architecture for the SDA. The PE-based architecture is very scalable and very flexible. We can reconfigure the PE dynamically, depending on the workload. That means that, and for example, there are several PE in the figure, and we can configure the PE number and the PE type. And in our architecture, one PE only implemented one operation. And the PE support all the data type in the TBCDS benchmark. I will take the filter PE as an example to demonstrate the microarchitecture. You can see the figure. The filter PE have the very highly parallel data path. It can process 8 rows of data concurrently. And it also can handle the comparison concurrently. And we implement the SDA by using the FPGA. This is the hardware board. The board is 4 height and half length, so it's feasible to deploy in the large-scale data center. It can be processed into the commodity server. And we're using the Silence KU115 FPGA. This is the first 20-nanometer FPGA, so it's very powerful. And we measure the real performance. A real power consumption is about 15 watts of the total power. And most of important is that the card has 4 channels, 17 2-bit DDR4. It runs at 2014 megahertz. As we know, the big data application is memory bandwidth bound, so we need more DDR channel and higher frequency. And the interface to host is PCIe. All the PE runs at 3 megahertz, and the design flow is RTL based. Although the RTL flow is engineered inefficient, but it can achieve very high performance and the power efficiency. We can see from the table that all the PE consumes lots of the BRAM. We use lots of the BRAM for the data locality, because the big data application is memory bound, so we use BLM to improve the memory access performance. And as I mentioned before, the SDA should be integrated into the distributed system. And the driver and API is the interface of the hardware and software. So they are very important for the project. The driver can configure PE according to the workload, configure the PE number and the kind of the PE, it allocate the queues for PE, and it maintain the views of the PE. And the lag figure is the API. I pick up two examples, the filter API and sort API is the C++. The next several slides is about the evaluation. This is the setup. The host machine is Xeon-based CPU. There are 12 cores. And the total memory size is 128 GB. We configured SDA 4 PE, each operation for 1 PE, and it runs at 300 MHz. We test the filter operation with variable data type and variable filter ratio. And we test the micro benchmark by using the dedicated C++ compilator. In the dedicated compilator, the comparison condition is written into the if statement, so the software code is very efficient. We can see that if the filter ratio is 19%, and and the data type is the long int, the SDA achieve 10 times better than the CPU core. When the length of data type increases, or when the filter ratio decreases, we can see that the performance of SDA decreases. That is because both this situation consume more DDR bandwidth, so the performance is limited by the DDR bandwidth. And we also test the carrier 3 of the TCP/DS in the SDA. We using the general C++ compilator. The general C++ compilator pass the condition firstly and then execute the comparison. So all the general purple platform using the general purple C++ compilator. We can see that the SDA can achieve 25 times better than the CPU core. This is one PE in the SDA, and the PE compilator is also general purpose, so I think the comparison is fair. We also test the sort performance. The test also with variable data type. We can see that when the data type is 7-byte LAN stream, the performance is best. The SDA is 13 times better than the CPU core. When the length of the data type increases, the performance scale is degraded because it's also limited by the DDR bandwidth. And we also test the Taylor sort in the SDA. The data format of the Taylor sort is standard. And we found that the 1 PE of SDA can achieve about 8 times better than 1 CPU core. We also run a real whole carrier from the TBC-DS. This is the carrier 3. We set the scale ratio to 10, and we run the carrier 3 on the SPARC in one server. And we also run the carrier 3 in the SDA. We can see that the SDA can achieve 5 times better than the SPARC on one server. And the right picture is the carrier code of carrier 3. So it combines lots of the operation, and it also has lots of variable data type. I think there are lots of the preliminary work on the SQL accelerating by using FPGA or using GPU. GPU is also very good at the sorting and some other operation. For example, the GTS T10 can achieve 500 megabyte per second performance. Under the data type is the int 64-bit on 1 megabyte data set. You can see the performance number on the NVIDIA website. And SDA can achieve 84 megabyte per second on the same configuration. And if we allocate 4 PE in the SDA, it can achieve about 336 megabyte per second. We can allocate more PE in the SDA, but the performance just increases slightly after 4 PE. It's also limited by the memory bandwidth. So the SDA can achieve 4 times performance efficiency than the GPU. And there are lots of the work on the accelerator for SQL kernel. But I think lots of the preliminary work only support a subset of the data type and the operation. And there's no work on the accelerator to run the whole TPCDS query. I think the GPU is very good at the regular data type, but for the irregular data type, for example, the variable length stream, I think the SDA is much better. And in the real workload, most of the key of the table is the variable length stream. For example, the city name, the people name, or the item name. So I think there are some advantage of the SDA. It supports all the data type of the TPCDS, and it's the general purpose accelerator. It supports the most operation of the TPCDS. And it also, according to the evaluation data, it can achieve very high performance. I think it benefits from the very high lambda memory access and the memory bandwidth and the data locality and the customized pipeline and ALU. This is the conclusion. We firstly present the general purpose big data accelerator. We abstract the SQL kernel and operation. And we also propose the SDA hardware and the software architecture. And we also implement the SDA hardware by the FPGA. And SDA is also designed for the distributed system. We use the data flow program model for SDA, and we can allocate the resource on demand. At last, we demonstrate the feasibility of SDA for the big data and for the AI. Thank you very much.
Thanks very much, Jian. We do have time for some questions. So let's start over here.
Well, this is an excellent talk to me. Thank you very much. Question here is, you have not touched on the application of this SDA in the automotive chips. Could you elaborate a little bit on that? And the second question is, do you see the possibility of implementing SDA in full custom silicon technology for...
You're asking the application in automotive?
Yep.
Did that, okay, just checking.
Yes. I mean, for autonomous car.
So the question is, are there applications in automotive?
Yes.
And what is the prospect or the benefits for more of a custom implementation rather than an FPGA?
You got it. Thank you.
Thank you. Automotive? Cars?
Oh. This project is only for the data center. only for data center. Yeah, in the car, I didn't need a SQL operation. And
if you run payroll in your car, it would be good.
And the second question is
what about a full custom implementation?
Chip?
A chip implementation rather than FPGA.
This is a very good question. You know, the data center application also integrate very quickly. So I think in this stage, we believe FPGA is the good choice. We can update the logic when the algorithm change or when the system change. Yes. Thank you very much.
All right, right here, please.
Hi, Jean Bosman with Hurwitz and Associates. Just a question, can you elaborate a little bit more about the data locality bullet that you just had? Just speak a little bit more about the importance of data locality.
Data locality.
Yeah, talk more about data.
Yeah, I can take an example. For example, for the sorting operation, we allocate lots of the on-chip VLAN for the inner sorting. Yes, if we can load more data into the chip and sorting them in the chip, the performance is better.
Well, that makes sense. Thank you.
Thank you.
All right, over here, please.
Hi, Paul Winslow, unaffiliated. Did you consider OpenCL for this type of problem set? And if so, why did you reject it?
Okay. We actually evaluate the tools of OpenCL, but I think for the very complex design, RTL flow is the best choice today. This is our conclusion.
Can you speak to if it was more efficiency, generally speaking, or memory accesses, or reloading those processing elements? Like which particular parts maybe made you reject it?
Sorry?
Can you repeat the question, please?
Yeah, I guess having looked at it some, I was wondering if parts of OpenCL that were limitations that you said, well, just general efficiency, or if it was swapping processing elements, or if it was direct access to memory, or things like that, that are the main drivers.
Yeah. If you rejected OpenCL, was it specific capabilities in OpenCL, like inefficiency in swapping, or other features or bottlenecks in OpenCL that drove that choice?
Okay, I see. The OpenCL is not very efficient for the larger scale design. And for example, if we use lots of the lookup table and lots of the other resource, the timing is a very critical problem. If we use OpenCL flow, it's very difficult for the timing close, but if we using RTL flow, I think they'll have a chance to close the timing. Thank you very much.
Thank you.
So one question you have answered about the OpenCL. So I have another question is from, so you guys, how to persuade your software engineer to co-design this application? Because many software engineers don't like using, they will hopefully design, handle their data.
Yes.
Yeah.
Good questions. Firstly, we are in the software team, so we are together. And secondly, we get the very bad performance, so they are happy to using the Accelerator. Thank you.
Thank you.
Right. Great. Let's thank Jian again.
Thank you.